Hello, everyone. Hello, everyone. How are y'all doing? Does anyone have any questions before we get started? Glad to see you're doing well, Nate.
I'm excited to see the new James Bond this Friday.
Ah, cool. Is it with the same guy still?
Yeah, this is his last James Bond.
I couldn't remember if this was his last one or if the last one was his last one and they already chose it. So yeah, I'm curious who they're going to choose next.
There's talk about Tom Hardy, and I'm like,
that don't seem right. Nah, I didn't care that much for Pierce Brosnan, honestly. He was a little too I don't know, just a feat or whatever, you know.
Understandable.
Didn't seem very masculine, which they haven't always been, but you know, Sean Connery and this dude definitely is. I can't remember his name to save my life, but he definitely is.
Daniel Craig.
Yeah, Craig, that's it. And I see Amy Farrah Fowler is still trying to win the Jeopardy role. Of course, it's not helping her doing stupid bogus medicine promotions commercials. Like,
I have not kept up with that. My dad and I watched Jeopardy every single day until he died. And after that, we stopped watching.
Yeah.
There's a lot of controversy of who's going to be hosting and what their past look like and all that stuff. So
it's kind of nerve-wracking to worry about that, you know?
Yeah.
They've had some cool hosts. I've liked a lot of them. I liked Aaron Rodgers, and I liked her name's Mayan Balak, but I always call her Amy Farrah Fowler or also Blossom. But I've liked a lot of them. Actually, that guy Ken Jennings or whatever his name was, he's pretty good. So, well, let's go ahead and get started until they make a new Simpsons movie or something cool like that. I don't have anything else important to talk about. One thing I want to mention to you guys, I was trying to stress to you in our last meeting about the importance of how you take a line integral. And again, this is one of those things, not unlike the partial derivative, where you're learning your math from someone other than a math instructor, and that's the nature of it when you're in science and engineering. So yeah, we learned the partial derivative in our error propagation lab. You learned a dot product, which hopefully you had in pre-calculus or trig or something like that. But now you've learned a line integral, which, to be honest with you, unless you happen to go to a really upper echelon university where the majority of the student body came in with calculus already, then you don't even get to that in Calc 3. That's often reserved and seen for the first time in advanced calculus. And then some people go so crazy and they make advanced calculus something other than really advanced calculus. They'll do, you know, number theory or some weird stuff like that. I finally got a chance to take an advanced calculus class one time, and the instructor completely changed the nature of the course to match this textbook he wanted to use, and it stunk. So we didn't get to do Green's theorem and all that cool stuff. So I dropped it. But anyway, so this is potentially a third semester topic from calculus, but again, we didn't get to cover it in my class, and I had a really good thorough Calc 1, 2, and 3 at a community college, but it was still a very thorough class, and we didn't get to cover it. So I'm going to go ahead and show you another instance. So last time we worked on the work done in compressing a spring, or actually I did it in stretching a spring. This time I'm going to do compressing a spring, because in this case you can see where I actually choose the direction of integration, and I'll do it two different ways. And both ways I'll get the right answer, but it'll show you what I mean by how you have to choose one way and then do something else about the other way. So let's start off. I'm going to imagine a spring. So let me turn my document cam on, or let y'all see my document cam. So imagine a wall and then a frictionless surface or nearly frictionless surface that a mass is sitting on. And let's say the mass is right here. And I'm going to put my y-axis right here, which means my origin's right there. And this will be my positive x-axis. Okay. Right now we have a spring that looks like that, okay? And we're at the origin. In other words, the top edge of the mass is at the origin. What I'm going to imagine is applying a force that's big enough to compress the spring, and it's going to go to the left, and it's going to be equal to K times X times I hat. And you might think, wait a second, that's going to the left. Shouldn't that be a negative? Well, remember, X is 0 here. So as I start to push further and further back, this X becomes negative. So that actually takes into account the direction by itself. So I don't have to write that F as in it's negative. And what's going to happen is the box is going to move way over to here. And I'm going to call that position negative X2. And I'm going to imagine the spring as if it's bunched up a lot tighter now. And looks like that. Okay. So now I'm going to calculate the work done in that, and I'm going to do it two different ways. So the first way is work is equal to the integral of f dot dl, as it always is. Okay. But in this first way, I'm going to let my direction of integration be defined by dl. And the rule is that you let either dl or the range of integration define the direction you're going. And whichever one you choose, the other one just has to go in the direction of increasing coordinate. So in this case, I'm going to choose dl to indicate my direction. And you'll see it as the integral of kx I hat, that's the force, dotted with, now since I'm going to the left, I'm going to indicate it by writing a negative dx I hat. Now, that means my range of integration just needs to go in the positive coordinate direction, which would be from negative x2 to 0. Okay, so that's the big deal here, is this one had to go in the positive coordinate direction since I was using this one to indicate the direction of integration. So what happens is the negative k comes out in front, and I get the integral from negative x2 to 0 of x dx times I hat dot I hat. We're using the linearity of the dot product there. Now we already know I hat dot I hat is 1, so that's easy peasy. And I'll get negative 1/2 k x squared from 0 to negative x2. Well, you can see that's going to be negative 1/2 k times 0 squared minus, actually technically minus negative x2 squared. So the answer is actually going to be this negative times that negative gives us a positive. So I get 1/2 k x2 squared. That's the work done. So that's one way of doing it. And it illustrates that, yeah, there is something to what I was telling you. It was not obvious before because I integrated this way, and then I did my range of integration that way too. So it looked like I was doubling up on them. If I doubled up on this, then I would have gotten clearly off by a negative. And you see this force is actually pushing the same way the object went. So that should come out to be a negative, a positive work as it did. If I had done it the other way, then it would have gave me a negative work, and that would be inconsistent because whenever the force has a component parallel to the actual motion that results, then that force should be a positive amount of work. We saw that last time with gravity and stuff like that. So now I'm going to do work the other way, where this way I let this indicated direction of integration. So that's what I did on this one. And this was just in positive coordinate direction. Okay, so now I'm going to do the other way. Let's say work is again equal to the integral of f dot dl. Again, the force is going to be kx I hat, because the x being less than or equal to 0 will make it be a negative. I'm going to dot that this time. I'm not going to use let the dl tell me which array I'm going to integrate. So I'm going to have to point it in the positive coordinate direction. So I'll just say dx I hat. Okay. Since I'm not telling you what direction I'm integrating with this one, that means I have to with this one. And the way I'm actually integrating is from x equals 0 to negative x2. So now I can say k times the integral of x dx I hat dot I hat. Again, that's just 1. And I get 1/2 k x squared from, again, 0 to negative x2, from 0 to negative x2. So in this case, you see you get 1/2 k negative x2 squared minus 0 squared, which again gives me 1/2 k x2 squared, which again is positive. So that's the deal on doing those line integrals. If you when you go to do them, you've got to choose a path, and that's normally chosen by you can use like a parametric version of a line in 3 dimensions, and then do the differential of it, and that'll become your DL. But in most cases, it's obvious. You can just do a DX or DR or something like that. So that was one example. Let me show you another example. This will be example 2. So we did an example with a force that depends on position, that depends on where you are along the curve, say. So let's do another one that we're now familiar with since we covered chapter 6. Let's imagine the Earth is right here, and we're at some point on the Earth, and the Earth's radius, of course, is r with that little plus in a circle. And I'm going to take off from here, and then I'm going to put a little break because I'm going to go a long ways and I can't fit it on the page. And I'm going to go all the way out to infinity. And I'd like to calculate the work done in lifting an object of mass m from r equals the radius of the Earth all the way out to infinity. Now, I will do this, and that'll give me the work done in moving the mass, but then I'll take our work energy theorem and say, what if that work was entirely done by a change in kinetic energy? And in fact, in order to do it, I had to travel at the speed of light initially to just come to a stop as I reached infinity. And lo and behold, we'll get a really cool result. So that's the 2 parts I'm trying. One is, what is the work done? And B, notice I said 1, what is the work done? And B, okay. How big must the Earth's radius be? And I'll put big in quotation marks. Big would Earth's radius be if the escape velocity, whoa, I want to spell escape with an X. That sounds reasonable, right? Of C, which equals 299,749,400, I think 749,000, 792,458 meters per second. Okay. This is supposed to be the word of. All right, so that's the other part of the question. And it actually gives us a really cool and accurate result, even though we're doing this all with classical physics. So that's why I thought I'd do it. One, it gets you to see another chance of working out the work for a variable force using the line integral. So what I'm going to do is I'm going to calculate the work. So this is part A. The work is going to be equal to the integral of F dot dl. Well, that force is going to be Newton's law of gravity. So, and in fact, it's got to point radially outward. So I'm going to use a convenient coordinate. I'm going to use the r hat vector, which is the r from spherical coordinates. you don't really have to worry yourself about what that is. I'll be glad to show it to you, or you can look it up on my YouTube channel because I worked that out. But it's all you need to know is that it's a unit vector and it points radially outward. So the force is going to be G times the mass the little object has times the mass of the Earth divided by the distance the object is away from the center of the Earth at any point in time. And then that's going to point in the r hat direction, meaning I've got to push it this way. Okay. And that's the r hat direction. Going straight away from the origin is the r hat direction. So there's my F. Now I'm going to dot that with my DL. Now I'm going to go from here out to infinity. So I can actually use my DL to indicate direction. And in which case I'd say it's dr r hat. Well, since I did that, now I just have to go in the order of increasing coordinate here, which is the same direction we're going. So it doesn't really harm anything. But I'm going to say I'm going from r, the radius of the Earth, to infinity. Okay. And this is something you usually don't cover. Maybe they'll cover it by the end of the second semester, but sometimes you don't see it until the third semester, range of infinity. But I think you do get it in the second semester usually. So again, we have a nice linear operation here. I'm going to write G and lowercase m and uppercase m for the Earth there. And now I'm going to write integral from r, the radius of the Earth, to infinity of dr over r squared, and then r hat dot r hat, which again, a hat means its magnitude is 1. So the dot product is supposed to be the magnitude times the cosine of the angle between them. So that'd be 1 times cosine of 0, which is 1. So this whole thing again is just equal to 1. So we get G m times negative 1 over r from r plus to infinity. So I'll show you how to handle that now. Now, that negative came from, this is basically r to the negative 2. The integral of r to the negative 2, you add 1 to the negative 2 to get negative 1, and then you divide it by the new exponent, which is negative 1. So that's why the negative came out here. So I'm going to say negative GM like that. Now I'm going to evaluate the range of integration. So I'd have to take the limit as r approaches infinity of 1 over r, and then subtract from that 1 over the other limit. So you can see the limit as r approaches infinity of 1 over r is clearly 0. And this negative combine to give you that the total work is a positive amount of work, and it's going to be GM over the radius of the Earth. So the work done is GM over the radius of the Earth, and that's our final answer, if you will. Any questions on that? Anybody not understand what we did there? Now, according to the work energy theorem, says that the net work, W net, is just equal to the change in kinetic energy. And remember, kinetic energy, which some books call T, by the way, is 1/2 mv squared. So what if this was the network required to escape Earth? In other words, to get out to infinity, but it's all going to come from the spaceship taking off, the spaceship of mass m taking off with a kinetic energy 1/2 mv squared, but it can only happen, let's say, if the speed was the speed of light. Then I'm sort of making the Earth into a black hole, right? That's the definition of a black hole, something so massive and so small that only light, and actually not even light, can escape it. So it sort of gives a lower limit on how heavy a black hole must be to be a black hole. So if I do that, then I'll say, okay, well, that means 1/2 mc squared, where c is the speed of light. Okay, that's going to be equal to gm times the mass of the Earth over the radius of the Earth. Okay, well, come to find out, even though we did this with Newtonian gravity, it turns out to be exactly the right formula for the source field radius. It's supposed to be a Z there. Sorry about that. SCHWARZ SCH, or excuse me, SCHIELD. No, it's just plain ILD. Sorry about that. Radius is solving for radius. I get R. In this case, it's the radius of the Earth if the Earth was a black hole, but I'm more giving you the general formula for the radius of a black hole would be, in fact, 2g times the mass of the body divided by c squared. So that's what I get by solving this for R. And it turns out, like I said, to be exactly the right formula for the source field radius. So let's calculate what that radius would be. So if the Earth really was small enough that something, meaning the radius was so small that the force of gravity was so large that only an object moving at the speed of light could escape it, then what would that radius have to be? And that's what we're calculating it. Well, it turns out to be 2 times 6.67 times 10 to the negative 11th. And that is, of course, Newton's meters squared per kilogram squared times the mass of the Earth, which is 5.38 times 10 to the 24th kilograms over 299,792,458 meters per second. That whole quantity, of course, has to be squared. And when I do that, let's calculate it. And I'll double check our mass of the Earth because I'm remembering that. The mass of the Earth is, oh, that's a problem. The mass of the Earth is 5.98, not 5.38. I'm confusing the decimal part for the radius part of the decimal. Okay, so it's 5.98. Sorry about that. So I'm going to do 2 times 6.67 e to the negative 11 times 5.98 e to the 24th. And now I'm going to divide that by 299,792,458 squared. And I get 8.8759 times 10 to the negative 3rd meters. And really, I only use 3 sig figs there, so I really shouldn't include these numbers. But I can make it into units of millimeters by getting rid of this 10 to the negative 3rd, and you'd see it's 8.88 millimeters. So if the Earth were 8.88 millimeters in radius, which is about that far, if it was that big in radius, or we could say this big in diameter, then the Earth would be a black hole. You can see that's about as wide as a little bit wider than my index finger. So if the Earth was that small, it would be a black hole. Isn't that cool? And it's cool because it's actually, even though I used the wrong methods, it turns out to be exactly the right answer. It's one of the happenstances where relativity and Newton's law of gravity work the same. Any questions on that? Okay, so that's some instances of using the work equals the integral of f dot dl definition. And I just ripped my paper. I really hate when I get these new pads because inevitably I discovered that some pads just do not rip or perforate properly. Makes me mad. Okay, so I have another example to work for you guys. Anybody have any questions on that one? Need me to show you anything on it? Hopefully the bandwidth is pretty good and you are getting decent images.
I'm gonna be honest, it is so blurry.
Is it really? That's
Yeah. I don't know if it's just me, but yeah, yeah, I can barely make out
it's
anything.
crystal. And so, well, at least that means the video will come out good when it's actually posted to YouTube. I will post it immediately after this, so probably within an hour it'll be posted. But yeah, I've got it. I was checking it. I put it back here again just to see if it looked that focus for me, and it looks really crystal on this side. So at least we got that coming. But I apologize if you need to see anything. Hopefully my wording was good enough to help you. But then also, of course, maybe this will help when you get to look back at it. You can see up close what happened to everything. And then ultimately I set 1/2 MC squared equal to that work. And I got the force field radius, and that gave me 8.88 millimeters. Sorry about that. I was hoping it'd be better. I suspect if it was bad for you, it was bad for everyone. So I apologize. All right, let's get another try. Now we have another example that I want to work. And this one I'm going to consider a softball. So it's not uncommon for a good collegiate softball pitcher to pitch well in excess of 60 miles per hour. So you might be curious, using the work energy theorem, can we calculate the work done in accelerating a softball? So this will be example 3. What is the work done? Oh, that's a triple U instead of a W. Okay, what is the work done in accelerating a 190.0 gram softball from 0 to 60.0 miles per hour? Okay, now I could ask for the power, and then I just have to tell you how long it took the person throwing it to go from 0 to 60. You could just take and divide that work by that time, and that would give you the average power. I didn't specify that, so we're not doing power, but I just wanted to make that addition, give you that additional information. So what we know is the 60 miles per hour is actually about 26.8 meters per second. So we've worked that out a bunch of times. So it's 26.8 meters per second. And what we know is that the net work done is equal to the change in kinetic energy. That's the work energy theorem. If we want to know the net work done, then I have to say what net work is equal to 1/2 mv final squared minus 1/2 mv initial squared, which of course is equal to 1/2 times 0.1900 kilograms. Notice I'm converting that to kilograms. The 1/2 and the m is common to both terms, so I'll put it in parentheses, factor this out, and this will be 26.8 meters per second squared minus 0 squared. Okay. When I do that, I end up getting about 68.28, or excuse me, 68.23 joules. Remember, a joule is about as much energy as it takes to lift a good, juicy, red, delicious apple up from the floor to the height of a dining room table, say. So this is about as much work as it takes to lift 68 of them. So you can sort of make sense of that, right? Basically, you're throwing so hard that this basketball, I mean, the softball that weighs comparable to a red delicious apple has to do about as much work as lifting it up to about a 32 inches or so. Any questions on that? Again, if I told you this happened in 0.2 seconds, then you could divide this by 0.2 and you'd end up getting 380 watts of power, but that's just another type of problem you can do. Any questions on that one? All right, well, let's visit our friend, the Tesla S-Plaid model again. So let's see, example 4. How much work, I'll make it like that, is required to accelerate the Model S-Plaid from 0 miles per hour to 60.0 miles per hour in 1.98 seconds, assuming its mass is 2,050 kilograms, 2,250 kilograms, say. Okay, 2, or let's say part B, so that'll be part A. Part B, what is the approximate power of that engine? Well, it's actually not an engine, so I should say engine, and then write actually it's a motor. Okay, so there's a big question. So again, I'm going to use the work energy theorem. I know that work net is equal to the change in kinetic energy. So that means the work net is equal to 1/2. Remember, always when you see a delta, it means final minus initial. So it's going to be equal to 1/2 m times v final squared minus v initial squared. So I'll put this in, I'll say 1 times 2,250 kilograms. And I Googled that to find out it's about 4,700 pounds, 4,766 pounds, which is about 2,250 kilograms. And then, of course, it's speeding up to 26.8 meters per second. And of course, that's minus 0 seconds, 0 meters per second squared. So when I do this calculation, I'm going to do 0.5 times 2,250 times 26.8 squared, and that gives me 808.02 times 10 to the third joules. So that's 808,000 joules, really. We use 3 sig figs, so both of these are extra digits. So I can say the work net is about 808 kilojoules. Whoa, or kilos. Now the power is pretty interesting because they actually advertise it or market it as 1,020 horsepower. So let's do part B and figure out what the power is on average. P on average is equal to the work done divided by the time taken. So you could say delta T if you want. Well, we learned that they did that in 1.98 seconds. So I can just take this 808.02 times 10 to the third joules, marking those two as not really significant digits, divided by 1.98 seconds. And I'm going to get 408.1, one extra digit, times 10 to the third watts, excuse me, I got ready to write joules there. But we know, if you look in the inside cover of your textbook, you will see that the unit of power, the horsepower, is 746 watts. So 1 horsepower equals 746 watts. So 408.1 times 10 to the third watts times 1 horsepower divided by 746 watts gives me, in this case, it turns out to be 547.0 horsepower. Okay. So there's a neat problem. Of course, like I said, they advertise that it's supposed to be 1,020 horsepower. This seems about twice as large. Did I remember to divide by 2 and all this stuff when I did it? 0.5 times 2250. Yeah, that all looks good. 0 to 60. Yeah, divided by 1.98. That looks good. Yeah, so it looks like that's actually quite a bit lower horsepower than they're claiming, but I suspect their 1,020 horsepower is probably, remember, like I told you, the acceleration probably is very rapid at first, and then it starts to wind down. I bet you if you analyze maybe the first half second of the motion, you'd find that it jumped to 0 to say 30 miles per hour in a lot less time than it took to get from 30 to 60 miles per hour. And if you did that analysis, then you'd probably find it's closer to 1,020 horsepower. So, any questions on that? Okay. Well, that's basically what all of chapter 7 is about. And we've essentially finished chapter 27. I've given you all the types of examples I wanted to make sure I give you. Some of the things you should keep in mind is that because work is defined in terms of a dot product, remember work, I gave you one version was F dot D, where D is the vector representing the displacement that was partly a result of this force F, but that's only true when the force doesn't change anywhere along the vector, along the distance D vector, okay? If the orientation of the force or the magnitude of the force changes anywhere along that D vector, then we have to use work equals the integral of F dot dl. And one of the results we got from that was work is equal to 1/2 k x squared, where this is the work done in stretching a spring from x equals 0 to x. Okay, all of these equations, whether they're numbered or not, are completely allowed on your equation sheet. And I think that one might not be. I'm confident this one is. I know 100% this one is. But for some reason, I looked earlier and I did not see this one counted. So I'm boxing it off now to let you know that it's completely okay to use these. Okay. So it looks like it is a consensus. Virtually everybody's agreeing that the video quality is not that great. And I am using my Ethernet. I do know that it's showing that it's running through the Ethernet cable. All right. Now, what I wanted to bring up next is conservation of energy, which brings us to begin chapter 8. So what I will tell you is that conservation of energy is the idea that there's certain types of energy that exist. The two forms of mechanical energy. So I'm going to say this is starting chapter 8, conservation of energy. Okay. And there's basically two types of mechanical energy. And we mean mechanical in the sense of mechanics, of like the mechanics of Newton. They all have units of joules. That's the normal unit that we use here, but they are kinetic energy, which is the energy of motion, okay? So kinetic energy, which is written Ke, K, or T, okay? That's the energy of motion. And generally speaking, that is 1/2 mv squared. I'll show you later that there's also a kinetic energy associated with rotating as opposed to just moving along a straight line. And the other one is potential energy. This is POTEN. I forget I have an eraser and I try to rewrite it over top of everything. It looks horrible. POTENTIAL, energy. Now they use a couple different symbols for this. They can say it's equal to U, or they can say it's equal to V, which is another thing that sometimes happens. But generally speaking, we're going to use U, and I think I recall that's what your book was using as well. Yes, U. Okay. It often, at least when you're close to the surface of the Earth, has a value. Oh, and also has PE. That's another way you can use it. Has a value given by M times G times H. So the potential energy for an object of height at a height H above the Earth's surface is the mass times the gravitational acceleration times the height H. So those are your two forms of mechanical energy. But in fact, there's actually a bunch of different types of potential energy. For instance, you probably heard of chemical potential. For instance, when you break a bond of, let's say, one of your organic molecules, you know, CnH2n+2. So any of those, when you break that carbon hydrogen bond, you get a certain amount of energy out of it. That energy that's holding them together is considered the chemical potential it has. And that's actually what runs a car, right? So there's lots of different types of potential energy. You can have potential energy due to being close to a nucleus of an atom, or you can have a potential energy due to two atoms being close to each other. You can have potential energy due to being too close to another nucleus or a particular particle having a nucleus, all sorts of different things like that. So there's a lot of different ways potential energy can come in. In fact, you can even think of the work done in compressing a spring as a potential, because when you push the spring in by an amount X, this amount of energy can come out of it given by 1/2 kx squared, and that has the potential to do work. So energy we think of as the ability to do work. And remember, I said work is anything that can drive a nail, and we examine the special case of a nail being, you know, one atom sharp and one atom in diameter, stabbing into something as soft as melted butter, right? So all I need is a force sustained over a distance like that, and that is a source of energy. So work is a source of energy. So when we talk about conservation of energy, there's a couple things you can do. You can say delta U plus delta K E is equal to 0. That's assuming that no work is being added to the system, right? That's a version of kinetic conservation of energy. It says the final potential energy minus the initial potential energy plus the final kinetic energy minus the initial kinetic energy all adds up to give you 0. And that is a perfectly reasonable way to define conservation of energy. And it works wonderfully as long as you're not putting work in or using any dissipative forces. You're not taking into account, for instance, friction, because it's negligible. If, however, you have any of those things, then you got to soup it up a little bit. And that's what I'm going to do, is I'm going to give you my souped up version. And not only that, students get a little, I hate one that, dang it, ripped it right now. Jesus, man. They're making me mad. Amazon ripped me off. There you go. Okay. So, anyways, students have a hard time remembering, for instance, in certain equations for potential energy, what means a negative amount, what means a positive amount. So what I started writing a long time ago was a different version of conservation of energy. And you're not going to find this in your book at all. What I would do is I would say the initial potential energy plus the initial kinetic energy plus the work you put into the system is equal to the final potential energy plus the final kinetic energy plus the work taken out of the system plus E loss. Okay, that's sort of a, I have a slot for everything that could happen equation. Okay, that's what I mean by that. So we actually, if we have conservation mechanical energy, then the only thing that's going to happen is these two are here. And notice if I pull the UF and the KEF over to that side, I get the original version that I had. All I've done is allow for you putting work into the system. So the system might be, for instance, a small child on a sled. Okay. And here's a little girl sitting on her sled. Okay. And maybe her dad gives her a little push or a big push because he's a sadist. Okay. He might actually push her with a force over a certain amount of distance, and that would be work put into the system. Then she's going to ride down the incline like this really, really fast. And you might want to know, what's her speed right here? Well, what you have is an initial potential energy given by M times G times H, where H is this height. Okay, so that would be the potential energy initial. And of course, I'm meaning that this is the height H. So I really shouldn't have drew the arrow with that. And in fact, I could then say, well, the initial kinetic energy was 0 because the father started pushing her at 0 speed, but the father did apply a force times the distance. So that could be F dot D right there. And then that would account for the girl getting to the bottom of the mountain and actually having a bigger speed than if she just slid down automatically. But what might happen is there might be enough snow here as opposed to nice hard stuff that there's a little bit of friction. If there's a little bit of friction, then this could be mu, the static friction force, F static, times the distance prime down the incline. So that E loss accounts for a loss in friction. Now, not only that, you might want to say, okay, I can now determine how fast you'll be going right here. But then at that second, they got a giant spring set up to keep the kids from running into, let's say, a chipper shredder. And, you know, commemoration of Fargo, the greatest movie ever. So just to protect the children, they have this nice spring set up. And in that case, the final kinetic energy would be 0, at least when the spring was completely compressed. But in this case, it'd be 1/2 kx squared, where k is the k of the spring and x is how much you compressed it. So by introducing conservation of energy with all these extra terms, you can solve a lot more problems. Okay. So let's imagine this. Let's say the little girl has a mass equal to 50 kilograms. I'll say 50.0, so we can always use 3 sig figs. Let's say the father puts in a force F equal to 100 newtons. Again, 100.0, so I can unambiguously say that's at least 3 sig figs. And he does so over a distance of, let's say, 2 meters, 2.00 meters. Let's say the entire length all the way up to here, that entire length, D prime, let's say that's 300 meters. Okay. And let's say the static coefficient of friction, mu sub static, is equal to 0.100. Okay. And we will say their average normal force, because notice when she's up here, her normal force will be her weight plus the weight of the sled, which I'm going to assume is part of that 50 kilograms. But when she gets on an incline, it's going to decrease to mg cosine theta. And then when it gets back here, it's going to go back to mg. So let's say the normal force is just 0.85 times m times g. Okay, so that's the way I can account for sort of the average friction over the entire slope. Okay, and let's say this K is equal to 10,000 newtons per meter. So, and I don't know why I wrote it so small. The K for the spring at the end is 10,000 newtons per meter, which we'll assume is actually 5 sig figs. And finally, let's say H is 300.0 meters. What I want to know is A, V, her velocity, just before hitting the spring. System. And I don't know why I'm using red, but anyways, I want to know her velocity. In other words, when she gets right here. And from here on out, it's just going to be the friction force so minor compared to the force of the spring. That's why I don't need to carry that any farther. So I just want to know what her velocity would be right here. And then part B, how much will she compress the spring? So that's our big problem. So let's start off with part A. So part A, I'm going to say her initial potential energy. Notice I'm writing UI plus KEI plus work in is equal to U final plus kinetic energy final plus work out plus E loss. That's the equation I'm using. Now, if I say the height is 300 meters, that by default means this height is 0. So that's going to give me a 0 potential energy on there. I don't always have to call that height the 0, but I have to find one and stick to that throughout the problem. So I'm going to write here 50.0 kilograms times 9.80 meters per second every second times 300.0 meters. That's going to be the initial kinetic, the initial potential energy. The initial kinetic energy is going to be 0 because I'm taking it from the instant that the father starts to push her. So she was at rest when the father started pushing her. So the initial kinetic energy is 0. Now the father, I'm assuming, is going to push actually parallel to the motion. So I'm going to say that's 100.0 newtons of force times 2.00 meters, and that's the work in. Now the final potential energy is going to be 0 because if I called this height 300 meters, then this height must be 0 meters. So since I called this 300 and said this is 0, then that height must be 0. So mgh is in fact 0. We haven't derived that, by the way. I just gave it to you. We'll derive it a little bit later, or you can see it in your book. And I want to know what the kinetic energy or what her velocity is. So I'm going to say plus 1/2 times 50.0 kilograms times V final squared. Plus, I got to take into account the E loss. I don't have to take into account the workout. And by the way, it's a little bit ambiguous which one's E loss, which one's workout. It doesn't matter as long as you count everything that's acting on it at least once, or exactly once, not at least once. So I'm treating this as compressing the spring, and I'm treating this as the energy loss due to friction. So I'm going to say the workout at this point is 0, but the E loss is actually going to be the work done against friction. So that's going to be 0.100 times, what did I say was the average normal force? 0.85 times 50.0 kilograms times 9.80 meters per second. That just gives me the force. Now I have to multiply that by 300 meters, so times 300.0 meters. So I know that's not a convenient way of doing it, but all these are multiplied by each other. So now let me take another step by doing these multiplications. So I'll say 50 times 9.8 times 300. That gives me a 147.0 times 10 to the third joules, plus 100 times 2 gives me 200.0 joules. So that takes care of that and that. And that's all equal to 25.00, extra digit there, kilograms times V final squared, plus, now I'm going to do the 0.1 times 0.85 times 50 times 9.8 times 300. And this one gives me 12.495 times 10 to the third joules. Okay. So this is the equivalent of this equation right here, is just this. So now I can see what I need to do. I'll say 147 plus the 200. So I'm going to say 147,000 plus 200. And then I'm going to say minus 12,495. That's going to give me 134,705. And that's, notice, joules for everything. Of course, these 3 digits are not significant. And that's equal to 25.00 kilograms times V final squared. So V final should actually be this divided by 25. And then take the square root of that, which is pretty darn fast. She's probably going to die, the poor child. It's the square root of 134,705 joules per 25.00 kilograms. That gives me 73.40 meters per second, which you could probably guess 60 miles per hour is 26.8. So twice that would be 52, and we're looking more like 73. So this is probably on the order of 150 miles per hour. So we'll just call that bad and say Mr. Younger has really done a horrible thing. You shouldn't think this out. Not really. It's the important part is actually getting a solution, because that's greater than 150 miles per hour. We wouldn't want our child doing that. This looks like, in fact, Christmas Vacation. So later, dudes. All right, now part B. Part B is, let's say now that she has that massive speed, she is going to ram into this nice, comfortable, soft spring mechanism to bring her to a stop. At that point, you could write this whole equation over again, or you can just realize, hey, basically I'm converting kinetic energy to work, and the work is going to be the 1/2 kx squared. So let me just set that up. So, and that's what I'm going to do. I'm going to say 1/2 of 50.0 kilograms times 73.40 meters per second squared is going to equal 1/2 of 10,000 point newtons per meter times x squared. Luckily, this 10,000 is a lot bigger than this 73 squared. Well, a little bit bigger. This is 100 squared, whereas that's 73 squared. So it's still going to be a pretty radical problem. So x is going to be equal to, notice the 1/2s actually cancel out. I don't have to do that. So I'm going to take 50 times the answer 73.40 squared. And then I'm going to divide that by 10,000. And I'm going to get x squared is equal to 26.941 meters squared. Those are extra digits. So in fact, x is going to be the square root of that. And I get 5.19 meters, which is a really unreasonable thing for a spring to do. But either way, that's basically what would happen with this type of problem. So you see, but this problem, and it's sort of something I make up every semester, is I make up some kid being pushed down an incline, just like this, so that I can make use of each of these terms. And that's really what conservation of energy is about. I've more or less covered the entirety of the types of problems you're going to solve, with the exception of there's some really highbrow mathematical rules that come from conservation laws. I'm going to hit on that a little bit, but we've basically hit every type of problem you can. The only thing you really need to understand is that the potential energy can mean a lot of different things, but if you're talking about height above the Earth's surface and you're not going, you're not going distances comparable to the radius of the Earth, then MGH is all the potential energy you need. Thank you. 163 miles per hour is what you got. Yeah, that's kind of bad. I just pushed my child into a spring-loaded piece of plywood at 163 miles per hour. That's terrible. All right, so I think that's enough for today. We have about 12 minutes left, but I think the rest of the stuff that I want to cover, I can't do it in the little 12 minutes we got left, and I think I'll just spot you this time. Yeah, part C, is she okay? I'll just spot you this time to start maybe finishing your test 3, which remember I did correct, and I did give y'all till Sunday to do, so maybe you can take your practice test a couple times. Maybe you can start waking up your equation sheet for your midterm, all that good stuff. I will wait for the last one of you to leave, and everybody's free to go.
Have a good night.
You too. Thank you for coming. Anybody have any questions? Matthew, Rebecca? All right, well, have a good one, folks. Bye.